In this podcast, I will be talking about molecular geometry, which is the three-dimensional shape of molecular compounds. We can predict the shape of a molecule based on VSEPR, which stands for valence shell electron pair repulsion. This theory says that electrons repel each other, therefore the molecules arrange themselves to maximize the distance for this repulsion. There are many different shapes, so we will just start from the beginning. The first group has two things attached to the central atom. To make things easier, I will use the formula AXE. A will be the central atom, X will be the number of bonding pairs, and E will be the number of lone pairs. The first shape is linear, AX2, so it has two bonding pairs. An example of a linear structure is carbon dioxide. First, we must find the Lewis dot structure. If done correctly, it should look like this. Notice that there are two things attached to the central atom, so that's how you know that it is linear. The next group has three things attached. The first shape in this group is trigonal planar, AX3, so it has three bonding pairs. An example of this is boron trifluoride. After the dot structure is made, we can see that it has three things attached, so it is trigonal planar. The second shape in this group is bent, AX2E1. An example of this is sulfur dioxide. The dot structure shows two bonding pairs and one lone pair of electrons. The next group has four things attached to the central atom. The first shape is tetrahedral. An example would be methane. It has four bonding pairs attached to the carbon. The second shape is trigonal pyramidal, AX3E1. Ammonia is an example of this. It has three bonding pairs and one lone pair. The last shape in this group is bent, AX2E2. This is different from the other bent because the other bent had one lone pair of electrons, while this bent has two. So the angles for this will be smaller than the angles for the other bent, since there are more things attached to the central atom. Looking at a molecule of water, we can see two bonding pairs and two lone pairs. Looking at the Lewis structure, you can see that the angles between the things attached is smaller since there are more things attached to the oxygen. The next group has five things attached. The first shape is trigonal bipyramidal, AX5. An example would be phosphorus pentafluoride. The dot structure shows five bonding pairs. The second shape is seesaw, AX4E1. Sulfur tetrafluoride is an example of a seesaw. It has four bonding pairs and one lone pair. The third shape is T-structure, AX3E2. This one's easy since the shape looks like a T. Looking at bromine trifluoride, we can see three bonding pairs and two lone pairs of electrons. The last shape in this group is linear, AX2E3. This is different from the other linear, since the other one was just AX2. It didn't have any lone pairs, while this one has three. An example is xenon difluoride. It has two bonding pairs and three lone pairs. Looking at the dot structure, you can see that the shape is slightly different. The angles are slightly different than the other linear. The last group has six things attached. The first shape is an octahedral, AX6. Sulfur hexafluoride is an example of an octahedral. It has six bonding pairs attached to the central atom. The second shape is pyramidal planar, AX5E1. Looking at bromine pentafluoride, we see five bonding pairs and one lone pair. The last shape is square planar, AX4E2. An example of this would be xenon tetrafluoride. It has 4 bonding pairs and 2 lone pairs of electrons. Now that is the last shape of the last group for molecular geometry. But I would like to end this podcast on a semi-fun note. So I'm going to be asking you a question. How is Casino Royale, the movie, like molecular geometry? You can pause it and think about it if you want, but I'm going to go ahead and tell you the answer. Now, only nerds will probably think this is funny. I thought it was really funny, but we'll just see what you think. So, how is Casino Royale like molecular geometry? They both have a bond following Vesper. Now this joke is credited to Nathan F. from Edmodo. Thank you, Nathan, for this hilarious joke. I thoroughly enjoyed it. I hope you did too. And this is the end of the podcast.